Hello and welcome to my lecture series on electromagnetism. Coordinate system, the most important topic for the students in science, engineering and technology. In general, the simplest coordinate system that we are familiar with, that is the rectangular coordinate system, or in other words, it's called the Cartesian coordinate system. In addition to this one, we generally do another two coordinate system. We generally use another two coordinate system. That is the cylindrical coordinate system and the spherical coordinate system. Now, how can we decide which coordinate system we should use and when to apply? Basically, it depends upon the type of problem, type of geometry over which the problem is defined. For example, if you tell your friend that your another friend went 1 kilometer or 10 kilometer from your current position, so your current position will be the origin of the geometry because you have referred your current position. But is that referring point is with the Cartesian coordinate or the cylindrical coordinate or the spherical coordinate? It depends that whether your friend moved along a straight line or a curved path or a curved path which is associated with a cylindrical type geometry or spherical type geometry. If it is just a simple straight line or a simple path, then you can use the Cartesian coordinate. On the other hand, if it's a curved path, you can either use the cylindrical coordinate system or the spherical coordinate system. But specifically, which type of coordinate system is the most appropriate and suitable one, that can be understood on the basis of another two features, that means the coordinate points. For example, in case of the Cartesian coordinate system, we define the coordinate point by x, y and z value. Similarly, in cylindrical coordinate system, we define the coordinate point by the radius of a cylinder, the circular angle of the radius with respect to the x-axis and the vertical z-axis. So z-axis for the cylindrical coordinate system and the Cartesian coordinate system both are equal to each other. On the other hand, for a spherical coordinate system, we use r, theta, phi. So I'm not going to discuss what are these r, theta, phi because I have dedicated another new lecture for the spherical coordinate systems here. Today in this lecture, I'm going to discuss only the cylindrical coordinate system and the relation between the cylindrical coordinate system with the Cartesian or rectangular coordinate system. So let's start. So in this lecture, I'll discuss the rectangular coordinate system because this is the most simplest one. You can refer, because if you can conceive the simplest one, you can easily understand the complex one. Next, the cylindrical coordinate system, and in the cylindrical coordinate system, the elementary length, surface and volume. That means how can we define a length, how can we define a surface, how can I define a volume, all those things. And the relation with the rectangular coordinate system with the cylindrical coordinate system. So first is the rectangular coordinate system or the Cartesian coordinate system. Here you can see that if you want to reach this particular point which has the coordinate as x, y and z, and this point is in the Cartesian coordinate system, so therefore you have to first move the length x along the x direction, then the length y along the y direction and along the y direction, and then the length z along the z direction. You may change the order, that means you can first move along the y direction, then the x, then the z, or from either from first along the z, then along the x, whatever. But when you are starting from the origin, you first have to move either along the x or along the y. You cannot directly jump along the z. But whatever, the movement can be altered, but you have to reach the length x, the length y and length z in order to reach this particular point, and that is why the coordinate system is defined as x, y, z for this particular point. And why it is rectangular coordinate system? Because as you can see that this point is can be think that it is placed on a surface of a cuboid. So in this way it is called the rectangular coordinate system. Now, what if you want to reach to another point from this particular point? Yeah, for that, look at here. So initially you were at this point xyz, and now you are going to, or you have reached the second point, which is x plus dx distance apart along the x-axis and y plus dy distance apart along the y-axis, and z plus dz distance away from the z-axis of, from the z-axis, not from the z coordinate of the first point. So therefore, how can we calculate, or how can we find what is the net displacement? That is very easy, because if you consider this one is one vector, suppose this is called r, and this one is another vector, this is called r dash. So easily I can define this vector as the r vector, or since if it is differential, I can write it is as dl. So therefore, I can easily write that dl is equals to x plus dx, comma y plus dy, comma z plus dz minus x, y and z. Therefore, the result will be, or the elementary length that you have to traverse in order to reach the second point from the first point is nothing but dx along the x direction, dy along the y direction, and dz along the z direction. It's very simple, I think. Now let's talk about the surfaces, elementary surfaces for the rectangular coordinate system. As you can see, I have marked three small tiny surface on each of the largest surface of this cuboid. Now, first of all, this dx represents the small tiny sample of the surface which has the surface normal along the x direction, along this direction, and it has the differential length along the y direction is dy, and the height along the z direction is dz. Therefore, the elementary length, or the elementary surface, or the infinitesimal surface along the x-axis can be defined as dy times dz with the x cap. dy is the length along the y-axis, dz is the height along the z-axis, and yx cap because this surface has the surface normal aligned with the positive x-axis, that's why s cap. Similarly, the dsy represents the elementary surface which has the surface normal along the positive y-axis, therefore y cap, and that can be understood by this expression as dx times dz, because this is the dx and this one is the dz. So dx times dz times this y cap, because it is along the y-axis. So now I think you can now tell me what will be the surface for the last one and the third one. That means this one dz. Obviously, the dz is dx times dy times z cap, because it has the surface normal along the z axis, and this length is along the y direction, and this length is the x direction. So this is the dx and this is the dy. So dx times dy. Now these surfaces has the direction, or the surface normal is along the positive z direction. But if I consider the same surface, but I'm considering the direction of the surface normal which is aligned along the negative y-axis or negative x-axis, or negative y-axis, or along the negative x-axis, or along the negative z-axis, in that case these surfaces will be defined in this way. So the magnitude will remain same for the positive x-axis, but since the negative x-axis I am considering, so basically I am considering the surface along the opposite direction for each of the surfaces. That means for x-axis, for this dx, I am considering the surface in the opposite side that I have considered for this one, that means for this surface along the positive z. Similarly for y direction and similarly for the z direction. And next is the elementary volume. Quite obvious that the elementary volume for this rectangular coordinate system will be product of dx times dy times dz. Now this quantity is a scalar quantity, because if you consider dx times dy, so the surface, it will be the vector and it has a surface normal along the z direction. So therefore I can write that dv is equals to dx times dy z cap dot dz z cap. And as you can see, since there is a dot product, so final result is dx dy and dz, and this dot product results in a scalar quantity, and we have the scalar quantity for the elementary volume of the rectangular coordinate system. And we will see later that the elementary volume for any type of coordinate system is basically a scalar. On the other hand, surfaces for any type of coordinate system is vector, because surface defines the direction along which direction the surface is defined. That's why obviously the direction is involved, but the volume is taking the all around the spaces of the surface or of the coordinate system that I'm defining or I'm using for a particular problem. Therefore, it is a scalar quantity. Now, the cylindrical coordinate system. Let's see what is the cylindrical coordinate system. As you can see, a cylindrical coordinate similar to the Cartesian coordinate system. If I defined a point on the cylindrical coordinate system, it means that basically I'm defining a point over a surface of a cylinder. And this is the origin. Now, if you want to reach this particular point, how can you reach? Starting from this origin, you have to move along the direction of the radius of the cylinder. As you can see, the coordinate of the cylinder is given as rho phi z. Rho is the radius for this particular cylinder over which this point is defined, or this is the destination point at which you want to reach. So in order to reach this point, you either have to move along this direction, rho, or you have to rotate along this direction first. Because why? If I say that you have to first move along the radius direction, so you can move either this direction or this direction or this direction or this, anywhere, because all of these directions are defined, or the radial direction, because you are moving along the radius of that. But except this one, if you move along any direction, you cannot reach this point. Because why? Because this one is making an angle phi, which is the coordinate defined over here with the x-axis. So this radius, which is making an angle phi with the x-axis, that is the coordinate of the second coordinate for this point. And after, so first of all, you have decided to reach at this point along the radius direction, but making an angle phi with respect to the x. Then you moved along the vertical direction by an amount z, and obviously you will reach over here. Therefore, if you want to reach any further or any other point other than this one, you can reach by changing the coordinate as shown over here. So therefore, rho can vary starting from 0 to infinity, because if you want to go far away in this particular coordinate system along the radius direction, so therefore rho can be any value starting from 0 to infinity. Phi, obviously, since it is the angle, it can rotate 0 to 360 degrees, so that's why 0 to 2 pi. And z, it can you can go either in negative direction along the z-axis or along the positive direction of the z-axis. So starting from minus infinity to plus infinity, you can move along the vertical direction. This one, that means the second diagram, is giving you the example where you are reaching the second point, which has the coordinate as rho plus d rho, the differential length you have moved to reach the second point along the radius direction. phi plus d phi, the differential angle or the infinitesimal angle you have moved further than you have moved earlier to reach the first point, and z plus dz, that means this dz amount, which is the differential length more than the z coordinate of the first point, you have to move over in order to reach the second point. As you can see that when you are going to reach this particular point, the second point from the first point, then along the radial direction you just need to move the d rho. So that's why the elementary length along the radial direction, which is d rho, that's a rho plus d rho. When you are moving along the z direction, the elementary length is the dz. But when you are moving along the angle, basically you are moving by making a curved path, and that curved path is followed by the surface, the curved surface of the cylinder, like this curved surface of the cylinder, like this. And that movement is not just the d phi, although the coordinate is phi plus d phi, but the physical length that you need to move along the curved path is rho d phi, because you should remember that when you are given a circle, and if it is the radius and this is also radius, and the angle these two radial direction is making, that is the d phi, then the physical length on the circumference of the circle is nothing but that rho times d phi. And when you are moving to reach the second point, you are basically moving over this circumference, traversing this arc, and that arc is rho times d phi. And that's why the differential length or the elementary length for the cylindrical coordinate system would be like that along the rho direction it's d rho, along the phi direction it is rho times d phi, and along the z direction it is just dz. Now the elementary surface. These are the surfaces projected from different directions, and this is a surface that you have seen when you cut your birthday cake with your friends, and such kind of piece you can take out of the cylindrical cake. Okay, so what type of surfaces then you extract, may happen that you may have not noticed at that time, but here I'm here to show you what are the surfaces you are extracting when you are cutting a cake at your friend's birthday or at your own. So there are basically three surfaces, as you can see. The surfaces are defined by its unit normal. So first of all, this one is the top surface, the red one. This one is the side, and this one is the front surface. This surface is defined along the opposite direction of the first one, and this one is also along the opposite direction of the first one. Now look at here, the surfaces as I have shown you in the case of Cartesian coordinate system. Here also the surfaces are identified by using their surface normals. The first one, the green surface, it has surface normal along the radial direction, because starting from here, if you move along this direction, this defines the radial direction. So it has a surface normal along the rho cap. On the other hand, the red ones, it has the surface normal z cap, and it has surface normal minus z cap. Similarly, this one is positive phi cap and this one is negative phi cap, because as you can see they are a bit curved, so it's along the phi direction. So this one is the phi cap and this one is the negative phi cap direction. Now what will be the magnitude of these surfaces? So first I'm considering the d rho, that means the along the rho direction. So what will be the surface? That can easily be understood, because if I take this sample surface, so this is along the curved path. So this curved path, the elementary path is rho d phi, and this length, the vertical length, is nothing but dz. So that's why this rho d phi times dz, and this surface, this elementary surface has a surface normal along the rho cap or along the radial direction. Now, the second surface, if I consider, that is along the phi direction, that means this one. So, if I consider a small elementary area for this, then this length is along the rho direction. For the infinitesimal length, I am considering d rho, and for the vertical direction, I do consider that is dz, and that's why d rho times dz, which has a surface normal along the phi cap direction or positive phi direction. Next is the third one, that is z cap. So the z cap has this vertical direction, and obviously a curved path, and this one here, that means this is the curved path, and this one, it defines the surface. Now this curved path is y, what, that is the rho d phi, and this length is what, it is d rho. So that's why d rho times rho d phi along the z cap direction, that is along the this direction. In a similar manner, the surfaces for the opposite direction should have the equal magnitude but opposite unit vectors for phi cap and z cap. But for the rho cap, there will not be any negative unit vector, because if you consider that if you want to take out a surface along this direction, and that will also be along the positive rho direction, because rho starts from 0 to infinity, no negative direction we do consider, because if a radius of a cylinder is 0, then the cylinder doesn't exist. Then the cylinder or the circle doesn't exist, okay, or it converts to a particular point. And the last one is the elementary volume. As you can see for the case of Cartesian coordinate system, where the volume was the scalar quantity, here also the volume is the scalar quantity, because if you multiply this d rho dz with the d rho d phi with the dz, so dz has its own direction along the z direction. Dz in this case is the length along the z direction. So rho d phi has its own direction along the z cap direction, and dz, which is the length, which also is directed along the z cap direction. And when you will take the dot product between this one surface and one path, that will result in the elementary volume, and that quantity will be the scalar quantity, as like the elementary volume that I have discussed for the Cartesian coordinate system. Next one is the relation with the rectangular coordinate system. So here, in order to express or in order to derive the relation between these, first of all, as you can see over here, I put this rho in order to mention that this rho defines the length of the vector along the rho direction, okay, and this phi represents the angle along the phi direction, and this is the length along the z direction, and this length and angle are defined as this rho, phi and z. On the other hand, the unit vector along the rho direction is rho cap. Unit vector along the phi direction is phi cap. Unit vector along the phi direction means, if you are interested to draw the unit vector at this particular point, so straight away draw a tangent at this point along the direction of phi, and that direction of the tangent will define the phi cap, as I have drawn over here. And at this particular point, the vertical direction, which has the length z, should have the unit vector as z cap. Now, in order to find out the relation with the rectangular coordinate system, I need to superimpose these rectangular coordinate system, that means x, y and z, at this particular point, in order to make you understand in much clear way. As you can see, I did it over here. Here, so this was the rho cap, phi cap and z cap. Now, this direction is the x cap direction, that means the original x direction. This one is the minus x cap direction, that is the original minus x cap direction. And this is the positive y cap direction, which is parallel to the original y direction, because this is the representation of the Cartesian coordinate system at this particular point I have drawn to make the comparison. Now, as we know, the x axis, y axis and z axis for the Cartesian coordinate system, they are mutually perpendicular to each other. In a similar manner, the rho direction or the rho axis and the phi axis and the z axis, they also are perpendicular mutual on each other. Although here is not an axis, that means the rho axis, not an phi axis, not an z axis, but the directions also, they follow the axis, should be perpendicular to each other. Therefore, as you know that phi angle is defined as the angle that the radius of the cylindrical coordinate system is making with the x-axis of the Cartesian coordinate system, and we also know that the angle between y-axis and x-axis is 90 degree. Therefore, if we define this angle as phi dash, then we also know the angle between the rho and phi is again 90 degree, and if this angle is the phi, so phi plus say x dash, or not x dash, phi plus say phi double dash is equals to 90 degree. And if you equate them, that phi plus phi dash is equals to phi dash plus phi double dash, so that will give you that phi dash is equals to this phi, and that's why I can define this angle as phi. Now they are related. Look at here. First of all, I'm going to calculate the length. That means this rho, z and this phi, how they are related along the for a coordinate point x, y and z. For example, as you can see, this is the x coordinate of a particular point on the Cartesian coordinate. This is the y point on the Cartesian coordinate. This is the z point. That means the point, if you define over here P, which has a coordinate as x, y and z. Okay. Now, if you define that P over a cylindrical coordinate system, then that would have the coordinate as rho, phi and z. So these are basically the length along the rho, along the phi and along the z. And similarly, this is the along the x, along the y and along the z. So how they are related? From this geometry, you can easily conclude that this x, this particular point, suppose this is the x point, x will be equals to rho times phi cap. This rho is the length, not the unit vector, not the unit vector. I repeat, it's not the unit vector. So rho times phi cos phi, y obviously the rho times sin phi, and z is equals to z, because the z axis in Cartesian coordinate system and the cylindrical coordinate system are equal to each other. Therefore, the rho square will be x square plus y square, because if you take the x square plus y square, rho square gets common, and cos phi square plus sin phi square will give you 1, and finally you will obtain this one. And if you divide this y by x, so you are going to get the tan phi, and finally phi is related with the y and x with this tan inverse of y by x. Now I am going to relate the unit vectors, which is the most important one. First of all, this rho cap. Now look at this diagram. Rho cap, when you align this x cap direction along the rho axis, rho cap direction, so obviously this x cap cos phi will be aligned along the rho cap direction. On the other hand, the y cap direction will be aligned with a sin phi, because this angle is phi, so therefore this angle will be sin phi. Next one is the phi cap direction. So this is the phi direction, and this minus x cap is actually aligned with the phi cap direction with a sine phi. So since this it is the minus x-axis, this minus x is appearing over here, and sine phi because the angle is defined in between the y-axis and phi axis, and that's why the cos phi is appearing when you are considering the alignment of y cap with the phi cap direction. And z cap is equals to z cap as usual. Now what if you want to find out the x cap and y cap in terms of the phi and rho? First, the x cap. It means that you need to align the rho cap along the x direction. So obviously it will be equals to the previous one, that means the rho cap cos phi. But what when you align this phi direction with the x cap, because the angle between the y and x is equals to 90 degree, and the phi, which is 90 plus phi angle away from this x-axis. So therefore you need to write cos of 90 plus phi cap, and that is equals to minus sine phi cap, and that is the thing I have included over here. So this is for the x-axis. Similarly, for the y-axis, the rho will be aligned with a sine phi and phi will be aligned with cos phi, and z cap will be equals to z cap. As simple as that. Next, the actual conversion between rectangular to cylindrical coordinate system. Conversion means here I have converted the unit vectors. Now, suppose a vector is given, a vector quantity, that means a, v, whatever, any arbitrary vector is given in rectangular coordinate system. How can you convert it into the cylindrical coordinate system? That is of our primary interest. So look at here. First, this a vector is given in terms of the Cartesian coordinate system, and here if you want to convert it into the cylindrical coordinate system, just replace its unit vectors by the unit vectors of the cylindrical coordinate system. That is, x cap I have obtained from this expression, I have just replaced over here. Y cap that I have obtained, I have replaced, and z, since z cap is equals to z cap for the both Cartesian and cylindrical, so there is no replacement is required. Now do a little rearrangement and couple all those terms which are associated with the rho cap and all those terms which are associated with the phi cap, and z cap will be equal to z cap. And now define that a rho is equals to ax cos phi plus ay sin phi, as you can see over here. So this is a rho, because in cylindrical coordinate system a vector is defined in this manner. So a rho must be related with ax and ay through this cos phi and sin phi. Similarly, a phi also will be related ay and ax through this expression, and az will be equals to az. Okay. This conversion process can also be obtained using the matrix method. As you can see over here, that the a rho, a phi and az, when you are going to relate with ax, ay and az, that means you are going to find out the representation in cylindrical coordinate system of a vector from the representation of a Cartesian coordinate system. So basically you are using this formula, and as you can see, this cos phi ax plus sin phi ay and 0 az, because it has no z component. And why we can represent this in matrix form? Because these transformation relation from the Cartesian to cylindrical and cylindrical to spherical, when I will discuss the spherical coordinate system, you will see that they form a linear equations, and that's why we can represent these transformations using the matrix form. In a similar manner, when I'm converting these from cylindrical coordinate system into the Cartesian coordinate system, so basically we have to take the inverse of these first matrix elements, and the conversion process takes place when you replace this rho cap from this expression of the x cap and y cap, similarly phi cap from the expression that I have obtained, and z cap also, z cap is equal to z cap. and that representation results in such kind of matrix. Just look at these two matrices, this first one and this one, because this is the inverse of this first one, and this inverse obviously will result this matrix. If you look at these two matrices, then you will clearly understand that the main difference between the two matrices is that the elements at the main diagonal of these two matrices remain same. On the other hand, the off diagonal elements of the both of these first matrix interchanges their places, and resulting in the second matrix. So what type of property these matrices are possessing, I will discuss later in this slide. Anyway, before going to discuss that thing, such kind of conversion can easily be done using the simplest form of this matrix, because you do not need to remember all these terms, where this cos form, where the cos phi will appear, where the sin phi will appear, where 0, where 1. You do not need to remember all these things. Just remember this matrix. This will be much more easier, because when you are going to relate ax with the all of this component of a row, just do this. So ax will be x cap dotted with arrow plus x cap dotted with a phi plus x cap dotted with az. Similarly, when you are interested to find this ay, y cap dotted with arrow, y cap dotted with the rho cap times the arrow, y cap dotted with the phi cap times the a phi, and y cap dotted with the z cap while it is multiplied with the az. Similarly for az. In a similar way, when you are interested to find this a rho, a phi and az, so you just have to take this inverse, and that inverse is nothing but, for this a row, this rho cap will be dotted with the x cap when it gets multiplied with this x cap, and this a row will be dotted with the y cap when it will be multiplied with this y cap, and this a row will be dotted with the z cap when it will be multiplied with the az cap. In a similar manner, this matrix you can arrange by yourself. This method is much more simplest one, rather than considering rather than remembering all these terms for this matrix. And now the most important part, that is, if I define this matrix as this MC, this matrix MC, as I told, the inverse of this matrix is nothing but just interchanging of their off diagonal elements. That means sin phi is appearing over here, and this minus sin phi is going over there, and all other term remains same. Such kind of matrix for which the inverse of matrix becomes the transpose of that matrix, because such kind of interchanging of off diagonal elements happen for the transpose of this matrix. But for those matrix which has the inverse of those matrix is equal to the transpose of itself or of its own matrix, those matrix are called the orthogonal matrix. And what are the orthogonal matrix? Orthogonal matrix means the element of this matrix are orthogonal on each other, and here you can see the elements are populated by either cos phi or sin phi. So cos phi is orthogonal over the sin phi. Orthogonal means the one which is perpendicular to other one. That means the cos phi and sin phi, they are 90 degree out of phase and they are perpendicular to each other, and that's why they are called the orthogonal matrix. And quite obvious, because in dealing with such kind of coordinate system, all the coordinate system that I have considered for both the Cartesian and the cylindrical coordinate system, the axes or the directions, they are orthogonal on each other. So this is a direct consequence that why we are getting the orthogonal matrix for such kind of conversion. Now the del operator in cylindrical coordinates. So this is a gradient. First of all, the gradient is described in this way in the cylindrical coordinate system. These are the standard forms. I am not going to prove all these things. When we need to use in the theory of electromagnetism, I will just apply these expressions directly over there, and I will calculate the divergence or the gradient for the cylindrical coordinate system, and this one is the curl for the cylindrical coordinate system, and this one is the Laplacian. Laplacian, as I already have discussed in my previous lecture, that it is the double derivative in three-dimensional space, but it has a physical significance. Till now, I didn't explain the physical significance of the Laplacian. I will discuss later in my lecture when I will discuss the potentials, electric potentials then. Now let's discuss a problem regarding these cylindrical coordinate system. You have given two vectors E and F. First, you have to calculate the magnitude of the cross product between E and F. It's very simple. Second one is that the vector component E at this particular point parallel to the line x equals to 2 and z equals to 3. So the component of the vector E you have to calculate which is parallel to this line and at this particular point. And the third one is the angle of E that makes with the surface at z equals to 3 at P. Okay. So let's start with the first one. So these two vectors are given, the cross product are very simple. Just use this matrix method, apply the matrix method, and here you will obtain the expression, and obviously the magnitude of that is equals to root over of 66 square plus that means the component square, and that will result in the 74.06. It's quite simple. Next one is that the second problem. That means the component of E, that is the electric field, this E, which is parallel to this axis. Now, parallel to this line, and that line is defined for x equals to 2 and z equals to 3. Now, this line is parallel to the y axis, and we have to calculate this electric field at this particular point. Now, since this line is parallel to the y axis, if I take the dot product of the y cap with the E cap, so that will give you the electric field that is parallel to the y axis. In turn, that will also be parallel to the y axis also. Therefore, so E dot y cap is our desired expression. But E is expressed in cylindrical coordinate system. Obviously, we need to replace this y cap into cylindrical coordinate system, and we know how to do that. Already we have obtained the expression for y cap, and that same thing I have replaced over here. And here, as per the question, that the point we need to calculate at this particular point P, where phi is defined as pi by 2. So just replace the phi as pi by 2 in this place, and you will get sin pi by 2 and cos pi by 2. So obviously this part will be 0, and y cap will be equals to the rho cap. So right now this Cartesian unit vector is converted into the cylindrical unit vector. So I can replace it as this one. Means E dot y cap will be equals to E dot rho cap, or we can get the minus 5, because this minus 5 is associated with the rho cap direction. Or equivalently, I can write this y cap, because y cap is itself the rho cap. And now the last question, that is, you have to find the angle the electric field is making with the surface which is defined at z equals to 3, and this length is equals to z is equals to 3. Therefore, this surface is extended up to infinity along the x-axis as well as along the y-axis, but it is limited at z equals to 3 along the z-axis, and that's why it defines a surface, not a line, not a volume other than a surface. Anyway, but this surface is making an angle 90 degree with the z-axis. So therefore, we can approach to solve this problem in such a way that first we can get a dot product of the electric field with the z-axis, so that we can get the angle the electric field is making with the z-axis, and that angle is theta. Say for, as you can see, the electric field direction is along this direction, and that's why it is an arbitrary direction I have drawn over here. So the electric field is making this angle theta with the z-axis, and as I have taken the dot product with the z, and that dot product will give you 3, and from here we can easily calculate, because the magnitude of the electric field can easily be calculated from this expression, and finally the theta can also be calculated. that is 74.98 degree, but that angle is the angle the electric field is making with the vertical z axis. But our requirement is to find out the angle the electric field is making with respect to the surface, and that is nothing but the 90 degree minus theta, because this surface is making an angle 90 degree with respect to the z axis. So simply subtract the angle that you have obtained from 90 degree and you will get your answer, that is 15.02. So that's all. In my next lecture, I will discuss the spherical coordinate system, which is the another interesting and most important coordinate system in when you are dealing with the electromagnetic theory. So till then, thank you very much.